dust. So imagine trying to take an image of coal dust at twilight, but it's even worse than that. So we had to worry about the necessity of using long exposures and the fact that the spacecraft scan platform is not a stable platform and always moves someone. Best image that we got, in fact, of the Uranian ring system, we had to use image motion compensation. What we saw in that image is a sheet of dust that extends throughout the Uranian ring system, and this sheet of dust is punctuated by features, many of them. There are more features in that picture than there are rings seen from inbound. So we have 9 narrow rings seen in the inbound images, and one newly discovered one, the Lambda ring.
As a matter of fact, if we had our choice, we never would have gone close to Miranda. In order to get to Neptune, we were obliged to go a particular distance from Uranus in order to get the right gravitational deflection on the spacecraft. Well, it turned out that that distance was exactly the distance that Miranda's orbit is from Uranus. It is a very exotic and complicated place. Most of the regions that we viewed are heavily cratered, old, rolling, ancient terrains. But embedded in these are very unusual circular patches, almost like racetracks, of groove terrains that run around in circular bands, surrounding very complicated crisscrossing structures in the interiors.
We addressed the question, what can we do to hear the data better? We did come up with a technique called arraying, where we took existing antennas and electronically wired them together so that, in fact, it had the appearance of being one larger antenna. And we did that in Australia, the primary receiving site at Uranus, and combined the DSN's stations with a borrowed antenna from the Australian radio astronomy community at Parkes.
Radio 5, Parkes 5. Stand by, Parkes.
While we were moving from Uranus to Neptune, on the ground we had 2 major things to do. First of all, we reprogrammed the software on board the spacecraft to do 2 things: to stabilize the spacecraft so that the pictures would not be smeared, and to add some new techniques to the spacecraft that would allow it to pan and track the planet when we were taking pictures near the planet. Second thing we had to do was improve the communications capability. We did that since Neptune is twice as far away from a communication standpoint as Uranus. We did that by enlarging the size of the antennas on the Earth and by adding several new sets of antennas into our deep space network to help compensate for the distance.
It is mission accomplished for Voyager 2. The space probe is headed out of the solar system tonight after photographing parts of the universe no one had ever seen before.
Now, we had some hints from Earth-based observations that Neptune had a few clouds, and at least that was better than Uranus. But we really weren't prepared for the spectacular weather activity that Voyager found. In fact, Neptune is the windiest planet in the solar system, and I was totally unprepared for that. The winds are 325 meters per second. That's the speed that the great dark spot is moving relative to the inside of Neptune. Everything's going to the east, but the great dark spot is going more slowly to the east than the inside of Neptune.
We had expected, because Neptune is not tipped on its side as a planet, but is an upright planet, that the magnetic field axis would be aligned with the rotation axis. That is, the poles would be near the rotational pole. We were surprised again. The magnetic field is tilted by 47 degrees in the case of Neptune, and its center of the magnetic field is offset by almost 2/3 of the radius of the planet. Its magnetic field is somewhat weaker, only about half of that of Saturn's, for instance, at the surface, and its magnetic field extends only about 400,000 miles from its surface. We did discover that the rotation period of the magnetic field is about 16 hours and 7 minutes, faster than Uranus, but slower than both Jupiter and Saturn.
Attitude Control. Go ahead. Yes, sir. I'd like to report that the scan platform is in the proper position as expected.
As we approached Neptune, we were approaching with the sun and the Earth almost directly behind us, so you could see virtually a full disk of Neptune. And we aimed to go right over the North Pole, right up over the top of Neptune, very, very close to Neptune. The trajectory was then bent by gravity, moved south, and we intercepted Triton while it was behind Neptune and underneath it.
Well, as we got closer and closer to Triton, it got smaller and smaller and smaller, and at the same time brighter and brighter. It turned out to be the brightest thing we've seen in the solar system. North of the polar cap, in the north, just above the equator, we find one thing we call the cantaloupe terrain. It has a system of crisscrossing ridges which produce a set of almost squarish to ovoid dimples throughout the surface. Now we're talking about a surface which is 37 degrees above absolute zero. This is the coldest thing in the solar system by far. Even the cold atmospheres of things like Neptune are warmer. It was unthinkable to find activity going on a planet whose surface temperature is that low. I mean, this is getting down to the point where molecules stop. It was about a month after the Voyager encounter that we were looking at stereo images way down in the southernmost part of Triton's polar cap, and we saw most of the features lined up as if they were on a perfect sphere. In fact, the two best examples turn out to be active eruptions in which material is being blown from the surface in a vertical column to an altitude of 8 kilometers, roughly 5 miles. Voyager discovered 6 new moons at Neptune. 2 of them were found in the ring arc or ring system, orbiting along 2 of the ring arcs. So apparently shepherding the edges of those ring arcs in some way.
When we look at Neptune's ring system, as we can see here in this mosaic, we see 3 continuous rings quite easily. There is an outer ring. It's the ring in which, in fact, the 3 arcs are embedded. There's an inner ring which, in high phase geometry, appears brighter than the outer ring. That tells us right away it's dustier than the outer ring. And then we see an inner, more diffuse ring at something like 42,000 kilometers from the center of the planet.
We believe now that we'll be able to communicate with Voyager essentially as long as it stays alive. 2 things will probably stop its life. First of all, it has a power source on board, which is a small nuclear power source called radioisotope thermal generators. And they operate by the radioactive decay of plutonium, which generates heat, which in turn is converted into electricity. In about 20 to 25 years, we expect to be low enough so that there's not enough power to keep the critical subsystems of the spacecraft operating. Or, at about the same time, we could possibly run out of attitude control fuel. That's the fuel which goes through little thrusters, which keeps the spacecraft stabilized and pointed at the Earth.
Now, between the stars, there's a dilute gas, ionized gas, filling interstellar space. It's called the interstellar medium. Each star blows a bubble in that interstellar gas. Our own sun does that. That bubble, in the case of our sun, is called the heliosphere. We don't know how large that bubble is. It may be that the distance to the edge of the bubble, called the heliopause, is 100 times the distance from the Earth to the sun. That is 3 times further than it is out to Neptune. In which case, 25 years, Voyager 1, which will at that point be 130 times as far from the sun as the Earth, could well be returning data from interstellar space for the first time. There will be a part of Earth which will roam essentially forever in the galaxy, and that will be the Voyager spacecraft.